Hi folks, welcome back to another live review session. This will be for the midterm for Calculus 1. And if you have any questions along the way, there's a chat box over on one of the sides of your screen there. Please ask questions in that chat box and I'll be happy to answer them along the way as well. So you're going to see a series of problems. This won't necessarily be all of the things you can see on the midterm, but it's the first part, and so give you a feel of some of the things that have been covered thus far. The other thing that will be included heavily actually on the exam is the chain rule. So please make sure you're aware of how to use the chain rule and be ready to go there. Okay, so without further ado, let's get started. We're going to evaluate the following limits. We have the limit as x approaches 4 of x cubed minus 64 divided by x squared minus 7x plus 12. So the first thing you can do is plug in 4 for both your x values on top and bottom, and what we can see when we do that, you'll get 0 over 0. Okay, so and if you don't, 4 cubed is 64, so you're good at 64 minus 64 is 0 up top, and then down below you get 16 minus 28 plus 12, that's 0 as well. So you have 0 over 0, so that means that's an indeterminate form. We have to do some work in order to get there. So what we can do though is, since we plugged in 4 and we ended up getting 0, that tells us something, and it's something quite important since these are polynomials. That tells us that we have x minus 4 as a factor of both the numerator and the denominator. So you have x minus 4 sitting there for both parts. The easier of the two probably is the denominator. That's x minus 4, and then that means you're going to have an x here. So what would multiply by negative 4 to give you 12? It would be negative 3, and then you could see that that adds up to negative 7. Negative 4 plus negative 3 gives you negative 7. Okay. The other one that might not be as familiar is we have a difference of cubes, and the way you factor that is you go a minus b, and then it goes a squared plus ab plus b squared. So you might not remember that one, but notice we have x cubed minus 64 is just 4 cubed, and so that means our a is x and our b is 4, so you get x minus 4. And then that means we have x squared plus x times 4 plus 4 squared. If you don't like this method, we could always divide by the factor of x minus 4. If you need practice with that polynomial division, just let me know and I'm happy to help. So this makes x squared plus 4x plus 16 over on that side. So hopefully that makes sense on that part. So now what does it allow us to do? Oh, I'm sorry. So part of this was cut off. Let me make sure. Does that look a little better? And hopefully that'll make sure you can see it says evaluate the following limits and all that jazz. So now moving forward from there, what do we have? Well, we get this thing becomes our x minus 4 is canceled, so we have the limit as x approaches 4 of x squared plus 4x plus 16, all divided by x minus 3. I'll erase this piece down here. And what does that give us? Well, now we can plug in and see if we get 0 over 0 again or not. And so notice we get 4 squared plus 4 times 4 plus 16, all divided by 4 minus 3. So our denominator is 1. So it's 16 times 3, which is 48 up top, I believe. And so our final answer is 48 for that one. Any questions on that? If so, please let me know. If not, we'll keep on chugging along. Okay. So now on to our next one. Limit as w approaches 9 of 9 minus w, and then we have 3 minus the square root of w. So, well, rather than write that there, first thing you could do I'll write it down below. Plug in. So what do we get? We get 0 up top because 9 minus 9 is 0, and then 3 minus the square root of 9. Square root of 9 is 3, so we get 0 over 0. So we have some work to do here once again. So since there's some work needing to be done, what actually happens? Well, we need to see with that square root, we need to try and solve that, and the way we do that is by multiplying by the conjugate of that denominator, but you can't just multiply the denominator by the conjugate. You need to also do that by the numerator. And the reason why we multiply by the conjugate, just an FYI, we have an a minus b essentially. If we take a plus b and multiply that, we'll get a squared minus b squared. So notice the b is the square root of w, so when we square that, the square root's gone. So that's essentially what the whole purpose of conjugation is just that difference of squares going on right there. Okay, so now what does that mean? Well, we have the limit as w approaches 9. We have 9 minus w up top along with 3 plus square root of w. And I just wrote it before, a minus b times a plus b, that's going to be a squared minus b squared. So that's going to be 3 squared minus the square root of w squared. So technically that becomes an absolute value of w, but since we're dealing with a positive number, we don't have to worry about that. So what we have is the limit as w approaches 9 of 9 minus w, 3 plus the square root of w, and down below that's 9 minus w. So notice our 9 minus w's are in common, so we can cancel those things out. And what we're left with is the limit as w approaches 9 of 3 plus the square root of w. And so what does that equal? Well, that's just 3 plus the square root of 9, which is also 3. And so our final answer is just 6. And we're done with that one. Okay, so we're going to move forward. If I don't see any questions, please ask them along the way once again. But if I don't see any questions, I'm just going to keep on moving. So moving forward to our next limit, we get the limit of this 9x squared minus 4x plus 19 all over the fourth root. Oh no, I'm seeing some of that. Oh yeah, it's showing up. Okay, partially. I might have to write it just a slight bit smaller. And so just to make sure. Sorry about that being cut off there. Hopefully we could see that now. 9x squared minus 4x plus 17. All over the fourth root of 81x to the 8th minus 17x to the 5th plus 3x plus 4. Now taking a look at this, what do we have to do? Well, the key to these things is you got to multiply by something. We can't just say x squared and then a fourth root of x to the 8th. What does that actually look like? You got to look at the degrees of the polynomials. And what I mean by that, and the degree of the polynomial up top is 2. And the degree of the polynomial inside the root is 8, but when you take the fourth root of that, that's like a degree being 2. Very similar to it. Okay. So what we'll do, there's one of two ways you can do this. You can factor out an x squared, or you can multiply both the top and bottom. That's the route I like to use personally. Multiply both the top and bottom by 1 over x squared. And if I go out of screen, please just give me a reminder every now and then. I'll try and keep everything kind of slanted downwards from here on out. So in the top part, when we multiply 1 over x squared times everything in there, notice here's what we'll get. We'll get the limit as x approaches infinity of, it becomes 9 minus, well, 4x times 1 over x squared would be 4 over x, and then 17 times 1 over x squared would be 17 over x squared. And we'll deal with that in just a minute. In a similar manner, we have this fourth root, and we have a whole bunch of stuff. 81x to the 8th minus 17x to the 5th plus 3x plus 4. But then we have 1 over x squared, and that can't go in there as is. So what we need to do is we need to convert it. Convert it to a fourth root of some kind. Well, in order for us to take that to a fourth root, we need to take this 1 over x squared and raise it to the fourth power. Okay, and so taking a look at that, so I see a question pop up here. Why do we multiply by 1 over x squared again? That's a great question. So the key, and I'll kind of highlight it here in red, is notice this 2 right here. That's the degree of the polynomial that we're dealing with. And then it's kind of hard to look at, but when you take this, the degree of what's underneath the root, you have a fourth root essentially of an x to the 8th. And so that's what I'm kind of noticing. When I take the fourth root of x to the 8th, that's an x squared as well. So that's the reason why it's 1 over x squared. Another way we could do this, by the way, what we could have done is factor out an x squared, or factor out an x to the 8th at the bottom. But so if you factor out an x squared, you're left with this 9 minus 4 over x plus 17 over x squared. Same song and dance. And what's going to happen in the bottom, if I factor out an x to the 8th, I could take a fourth root of x to the 8th, which is what we're about to see here in a second. And we'll be left with 81 minus 17 over x cubed plus 3 over x to the 7th, and then plus 4 over x to the 8th. And so essentially what's going to happen is this fourth root of x to the 8th, that's becoming x squared, and your x squareds will cancel. So this would cancel off with that, and then you're left with what's remaining right here. Hopefully that makes sense. If not, let me know. But so that's all we're doing is just another format. You might have seen this route, you might have seen the other route. Whatever works for you, I'm fine with either method. But both methods work. The key, though, was the degree. I just looked at the degree of the polynomials involved and then work from there. And that's pretty much going to tell you all the time. If they become, so the roots do cause some confusion, but really when you take a fourth root of x to the 8th, that becomes x squared, and that's essentially the degree of your numerator. So that's where we got away with that. Does that make sense on that part, Jalen? Please let me know. If not, I'll be happy to kind of try and clear it up a little bit more. But it's always coming down to the degree. So now, moving forward on what we have before, we can rewrite that. When we raise it to the fourth power, that becomes the fourth root of 1 over x to the 8th, which is, what do you know, exactly what we were kind of doing over on the other side. So, awesome. I'm glad to hear that made a lot more sense there. I'm glad to see you asking questions. That's what I'm here for. So that's the main purpose of this too. So now what we have is 9 minus 4 over x plus 17 over x squared. All over. Now when we take that 1 over x to the 8th, inside there you'll actually see even more how this works to be the same. This is the fourth root of 81 minus 17 over x cubed. And then plus 3 over x to the 7th. Then plus 4 over x to the 8th. Okay? Now, beautiful thing happens. And I'll erase that part. We'll work the other way. Sorry for kind of going backtracking, but I was trying to keep that up. Where you could see that those two things would be the same. Excuse me. Okay, so what happens? Well, as x goes to infinity, 9 is not going to be affected, but as you have 4 over some really large number, that large number is going to go to 0. Same thing with 17 over x squared. As that bottom gets, the denominator gets to be closer and closer to infinity, that thing's going closer and closer to 0. Same thing with all these. Each and every single one of those goes to dun, 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 0, right? So what this thing becomes is the numerator is just 9 minus 0 plus 0. The denominator is the fourth root of 81 minus 0 plus 0 plus 0. And that whole thing equals the 9 divided by the fourth root of 81. So what number raised to the fourth power equals 81? That would be 3 to the fourth power, because 3 squared is 9, and then 3 to the fourth would be 81. So this is 9 divided by 3, so our final answer is 3. Surprise, surprise. 3 was a magic number here. So hopefully that makes sense on that problem. If not, let me know. That's what I'm here for. So, but that's the whole process with these. You look at the degrees and then you can kind of work from there. Okay, this next one, a trig limit. My strongest suggestion would be to first write this tangent of 2 theta as sine over cosine. So this is the limit as theta equals 0, or theta approaches 0, not equals 0. Oh, I should, what do we do first? You plug it in. And the reason why we didn't plug it in right away on the last one, you had infinity, so you knew you had to do work. But you plug in 0 in for tangent of 0 is just 0, so you have 0 over 0, so we need some work. So in this case, we have sine of 2 theta over theta, and then there's a cosine of 2 theta, right? Because tangent is just sine over cosine, and since there's 2 theta going there, we're good to go. Now, we can break up limits into separate limits, so that's kind of useful. You can go limit as theta approaches 0 of sine of 2 theta over theta times the limit as theta approaches 0 of 1 over cosine of 2 theta. Now, something we can kind of make use of, if you have the limit as x approaches 0 of sine of x over x, that actually equals 1. I know that doesn't seem right, but that's the way it works. So, but instead of x, notice we've replaced the inside with 2 theta here. So that means we need a 2 theta down below. So in order to do that, what we'll do is we'll do a sneaky trick here. We'll write this as a 2 and a 2 here. And so what we can do is we could take this 2, remember we can move them, constants out in front. We'll move that constant right out there, so you get 2 times the limit as theta approaches 0 of sine of 2 theta. Now we'll take this 2 and just move it right there. Because of multiplication, we can do this. And then times the limit as theta approaches 0 of 1 over cosine. So 1 over cosine of 0, we'll talk about that in just a second. Okay, and so this is something else. But we know that this part right here, so this equals 1, right? So this thing just becomes 2 times 1 times 1 over cosine of 0 is just 1. So our final answer is actually 2. And we're done. Questions on that one? Kind of tricky with trig limits, but you can do that song and dance and get in pretty good shape. Okay. And so now on to our next one. Let's see. Let me scroll that up. Hopefully we can see that coming up on our next one. So we have the limit as x approaches 0 of x squared cosine of 7x plus 1 over x to the 4th minus 3x cubed. So notice when we plug in for the cosine, you get cosine of 1 over 0. Have no idea what that's approaching. And then we have x squared, which is 0. So 0 times something we don't know, that doesn't quite tell us what it's going to be. So we need to do work on this one. In this one, though, we need to take note. The nice part about this is that this is bounded. When you have cosines or sines, those things are bounded. That's a beautiful result that we're going to make use of here. So we get -1 is less than or equal to cosine of 7x plus 1 divided by x to the 4th minus 3x squared, right? And that's less than or equal to 1. Why is that so useful? Well, what we can do is multiply both sides by x squared. So you get negative x squared is less than or equal to, we'll put an x squared in here, cosine of 7x plus 1. And then we have an x to the 4th minus 3x squared. And that's less than or equal to 1 times x squared. Now the other thing I'll toss on each side is just a limit as x approaches 0. Does anyone know the name of what we're about to use here? Any ideas, any takers? Please just insert it in there if you think you know it. What are we going to be using? And so we've used that bounded part. There's a big theorem that we're about to use here. And so notice that you have this thing equals, the limit as x approaches 0 of negative x squared. If you plug in 0, you get 0 there. And if you look at the right hand side, limit as x approaches 0 of x squared, that also equals 0. So what do we think the limit of the interior is? Any guesses? So actually this limit as x approaches 0 of x squared cosine of 7x plus 1 all over x to the fourth minus 3x squared, that thing actually equals 0. And then there's the main reason that you're going to have to be able to state is by the squeeze theorem, right? So the main thing is try and be able to understand why these things occur and why they happen. And so that's exactly it. In this case, this is by the squeeze theorem, and so we're done. Okay. Now, let's take a look at this last one. This trips up a lot of people. So, for our last one, we have a limit as x goes to infinity. We have square roots involved, right? So, yeah, it is squeeze. I see that pop up. And Jalen, you got it just in time. I just noticed. So, just shoot me an email. I'll give you a bonus point towards that homework, so for getting it. Yeah, as long as you answer a question along the way, if you answer it in time, first one to answer, I'll give you credit for it. So keep that in mind for future references if I'm asking questions during these reviews. So great job getting the squeeze theorem. Yep, that's exactly what we want to see. So in terms of our next one, we have the limit as x goes to infinity of the square root of x squared plus 5x minus the square root of x squared plus 3x. If you plug in infinity, you get infinity minus infinity, which is an indeterminate form once again. So we got to do some work. So the only work we really can do is think about it. If you have an a minus b, we want to get rid of these square roots. So you got to go times a plus b, which equals a squared minus b squared. That's kind of the idea that we're going to use here. Except the way we're going to do it in this time, we got to make a fraction. We can't just multiply willy-nilly by what we want. That changes the limit. So we got to do, if we're doing it in a numerator, which is where this will be applied because it's essentially like a numerator, then we also need to do it in the denominator there. So I see a question that just popped up. Yeah, so great question. Do we need to put by the squeeze theorem every time we solve a problem using it? Most definitely. If it comes to exam time, you should put, when you're using the squeeze theorem, by the squeeze theorem, right? And things like that if that's your limit. Now, don't just, so I call it carpet bombing. So some people get in the habit, oh, I'll just put squeeze theorem on everything. That's a different story. I want to make sure you can explain yourself, because really in real life, that's what you need to be able to do. Is if you're solving a problem, you need to be able to explain yourself, and so that's what we're kind of looking for here. The solution, that's hunky-dory, but it's the explanation that we're kind of wanting to see too. Okay, does that make sense and answer your question then? Just let me know if you still have more questions on it. But yeah, if you see something like that, the key with squeeze theorems, I would say just try and find a bounded function. So notice this one we had, it was the cosine's bounded. Even though that function's nasty, we can bound it versus, and let me relate it back to before. On this one, the tangent of 2 theta over theta, that was a trig limit that we knew. So there's no bounding going on in this one. And dividing by 0, that's really going to just make things even more unbounded, versus the other one where you're multiplying by 0, that's kind of an indicator that we're dealing with a squeeze theorem in some form or another. Hopefully that makes sense. That's the trickiest part for people to distinguish. But once you get that down, it does get a lot easier, I promise you that. So, and yeah, keep the questions coming, folks. That's what I'm here for. So in terms of this one, we have the square roots. Notice the square roots will now go away, magically disappear, right? So you get limit as x approaches infinity of, so I'll actually write out the extra step for right now. Square root of x squared plus 5x, and then we're going to square that piece. That's the whole purpose of this. And see, this conjugating, it happens quite frequently. But the difference is you see the square roots appear on the outside of a term, right? So like, what do I mean by that? So you have a plus or minus where the square root is not continued, unlike the other page where we had it just one whole square root or fourth root on the bottom. So that's the big difference on these. So this becomes what? Square root of x squared plus 5x plus the square root of x squared plus 3x. Okay. The fun is about to begin. We get the limit as x approaches infinity. What do we have here? So this becomes x squared plus 5x minus, make sure to put that last piece in parentheses since it's the whole part, x squared plus 3x. That's the tricky part for a lot of people. So you get x squared plus 5x underneath that square root, and then we have a plus square root of x squared plus 3x. Okay, so the numerator, what does that become? So we get limit as x approaches infinity of, notice your x squareds will cancel. In 5x, we have to go minus that 3x, right? So 5x minus 3x is just 2x. And notice now what we have down below, we have square root of x squared plus 5x plus the square root of x squared plus 3x. So what is the degree of our numerator, and then what would the degree be of the denominator? Right? Essentially, it's tricky on the denominator because you have a polynomial on side a root, but if you look, you have a square root of x squared. What does that kind of simplify to? And then in the other case, what's the degree of that numerator? Let's take a look, because that's what we'll essentially multiply by. So we'll go 1 over whatever x to whatever power that would be, and 1 over whatever x to whatever power we have for that denominator. Well, in our numerator, the degree is just 1, so we'll just put 1 over x to the first power, or you can just leave it as 1 over x. And the denominator, square root of x squared, that reduces down to 1 as well. So now the nice part, I'll kind of do a Texas 2 step here. In the denominator, the square root of 1 over x squared is the same as 1 over x. So we'll write it that way. That'll allow us to distribute this to both parts. Okay, so this thing becomes the limit as x goes to infinity of, well, when you multiply this on over 1 over x times 2x, that just becomes 2 up top. Now, just an FYI, that is the square root of 1 over x squared. So everything inside these little square roots, we're going to multiply this times each piece. So what does that become? Well, when we have 1 over x squared times x squared, that's the square root of just 1. Plus 5x times 1 over x squared is just 5 over x. And then x squared, once again, times 1 over x squared is just 1. Plus our other piece is just 3 over x. Okay, so most of this 5 over x is going to go to 0. This 3 over x is going to go to 0. So what we're left with is just 2 over the square root of 1 plus the square root of 1. Right? So it's going to be 2 over 2, which means our final answer to this, and I don't think this was something we saw coming, is just 1. Okay? Questions on that one? I know that one's pretty tricky, but I wanted you to see a tricky one because that's all fair game in terms of what we do. Okay, so in terms of limits, that gets us going, and now we're going to move into some continuity and some other things along the way, some of those more particular questions. How do we handle those?
So for this one, for what values of the constant c is the function f of x equals cx squared plus cx if x is less than 1 and c squared x if x is greater than 1 continuous on negative infinity to infinity? So the only problem point you can kind of see is going to be when x equals 1, right? And the reason is, so here's what we need. We need the limit as x approaches 1 from the left of f of x to equal the limit as x approaches 1 from the right of f of x. And the reason why is because we need the, first off, the limit as x approaches 1 of f of x to exist, and that has to equal f of 1 for it to be continuous, right? F of 1, by the way, just an FYI, according to that, up above, it should be c squared times 1, right? And we got that from the second condition, so all I did is use this right here. Okay. Now the limit as x approaches 1, we need the left and right hand limit to be equal in order for that to exist. So that's why we need all these parts to kind of come into play. Okay. So now taking a look. So what is the left hand limit? Well, our left hand limit should be, we're going to use, and let me put a couple squiggly lines right there. We're going to use that top equation. So this would be c times 1 squared plus c times 1. And our right hand limit should be just c squared times 1. And notice the beautiful thing here is that is just f of 1 as well. Okay? So keeping that in mind, notice we get 2c equals c squared. Now most people would solve this by saying, oh, let's divide by c, but you actually lose a solution along the way. So what I do, this is a quadratic, so you subtract the 2c from both sides. You get c squared minus 2c. Notice that both have a factor of c. So you get c, and then you get c minus 2 as your factors. So that means that you have c equals 0, and c minus 2 equals 0, so c equals 2 is your other factor. So your solutions to this are c equals 0 and 2. And you can understand that that's going to also work for this limit. When c equals 0 or c equals 2, you get this limit as x approaches 1 to exist. Questions on that one? So it's always left and right hand limit dependent on when you have the piecewise function trying to piece it together and find that constant. Sometimes you might have to add in that extra fact that the function value, what it is, if you have maybe 3 parts to a piecewise function, and where left and right hand limit, and then you have the function value all being involved. So just be aware on all that song and dance. Alright, so our next one, fun times. We're going to be dealing with graphing. So what we want to do with our next one here, we're going to sketch the graph of a function f that satisfies all of the following conditions. So we have limit as x approaches negative 2 equals negative infinity. Limit as x approaches 0 from the left equals positive infinity. Limit as x approaches 0 from the right of f of x equals negative 3. Limit as x approaches 3 of f of x equals 1. Limit, and then we have f of 3 equals negative 2. Limit as x approaches 5 from the left of f of x equals negative 4. Limit as x approaches 5 from the right of f of x equals 3. Limit as x approaches infinity equals negative 1. And limit as x approaches negative infinity equals positive 4. Whew, a lot of work, but I think we could do it. So let's see here. I'll put in some tick marks so we can kind of mark this off. There's a lot of empty space that we're going to be dealing with too. Okay. Alright, so the easiest parts I'd say actually to do, first off, I'll box them kind of as we do them. this f of 3 equals negative 2. That's easy, right? So what do? We go 1, 2, 3 units, and we go negative 2, so that means we put a dot right there. Okay, so that's f of 3 equals negative 2, so that one's done. Now, is there another one where we have a function value? Well, no. Okay, so now that that's done, that's the only piece that we have to put in the graph for sure with a solid dot. The rest, sometimes you can avoid solid dots and altogether. And sometimes you're going to have freedom. So notice this actually reads from left to right, with the exception of the negative infinity. We'll deal with that in a second. But we have limit as x approaches negative 2 equals negative infinity. So what that means, first off, and let me draw the graph in blue, but I'll put black to kind of give myself little markers here along the way. So notice we have at negative 2, this is x equals negative 2. What must happen? Oh, and one other comment. This is a function, right? So since it's a function, it should always pass the vertical line test. So if you ever draw a graph and it's a vertical line would hit the graph more than once, you no longer have a function. So that's something you always have to pay attention to. Okay, keep that in mind. So with that being said, we have limit as x approaches negative 2 equals negative infinity. So that means as we approach this thing from the left hand side, we go towards negative infinity. Who knows where the rest of the graph will go? And then when we approach it from the right hand side, we get negative infinity. Okay? So, and this stuff will come in handy later. We're going to actually sketch full graphs of the curves just based upon this and some derivatives and something called a second derivative. We can actually draw the whole graph. So now the next piece, limit as x approaches 0 from the left of x equals positive infinity. So that means we have to go, and as we approach 0 from the left, which is just the y-axis, still passing the vertical line test, we get something like that. So now I need to connect those two spots because there's nothing else in between, and so I'll draw it that way. Don't let your eyes fool you. That was not intended for it to fail the vertical line test there either. Okay. Sorry, my pen slips a little bit every now and then. Now, a little more interesting on 0 from the right. Notice we have, as we approach 0 from the right, we get negative 3. So there's actually some options here. I could put a solid dot because I don't have any 0 value, or I could put a hollow dot, an open dot. So I'll have to, in this case, I'll just put an open dot. It isn't going to hurt. And we'll approach it. Now I can approach it from down below or up above. It doesn't really matter. I'll go down. Because there's nothing else saying it has to be increasing or decreasing from that point. But now what we do have is we have the limit as x approaches 3 of f of x equals 1. Now here's where we should put an open dot, because notice f of 3 equals 2. In order for this to pass the vertical line test, we need this to be a hollow dot. So we'll put an open circle right there, and somehow I have to take the graph from that point all the way up. And I'll even come in from this angle. That's fine. It doesn't make a difference on which side I come from, but as long as I still pass that vertical line test, we're in good shape. And I have to also come out the other side, so I'll come out there. Okay, so now as we approach 5 from the left, we have to be at negative 4. So let's go down below, and here's 5, and then there's negative 4. I'll put a circle here, and we'll go on that side, so that gets 5 from the left, whereas 5 from the right is positive 3, so we'll go 1, 2, and 3. Now I'll put a circle there, 5 from the right, boom. So that takes care of that piece. Now if we want, though, there's nothing about 5 from the right or left, so it doesn't matter which side. I'll just for kicks, I'm going to fill in this with a solid dot, just for fun. But you had options there. Now, moving forward from this part, limit as x approaches infinity equals negative 1. So what happens is, as we go off to infinity, we get towards negative 1. So we'll go off towards infinity, and we're getting closer and closer to negative 1. So that takes care of this piece. And so last but certainly not least, notice we need the left-hand side of our graph taken care of. Limit as x approaches negative infinity equals positive 4. So we'll go 1, 2, 3, and then 4. And so we'll take the graph on up, and we'll draw it that way. And that takes care of this piece. Is this graph unique? No, by no means. The only things, and I'll highlight it in red real quick here. So the red portions that you see are the only pieces that we really needed to have in there. Oops, that red is supposed to go right there. Doesn't have to be an open circle. Could also have been a solid dot, but I'll put that piece. We'll need pieces. Doesn't need to be from above or below on this side, but we need that as we approach it. 3. We needed to approach from here. We needed to approach from there. And then we need the 2 endpoints. What does that mean? Everything that's not red, it means it's open to interpretation. You get a lot of freedom with this graph, okay? But so just those little pieces in red kind of show you what's going to happen in terms of what you needed to draw the graph, okay? Hopefully that makes sense on that one. You'll see that happen pretty frequently. We'll deal with stuff similar to this from here on out, especially Module 3. You'll see a lot of this stuff. Okay. So let's see on our next one. Ooh, this one's kind of fun. Does there exist a number that is exactly one more than its cube? Justify your answer. So this seems kind of random, really, and especially we don't have a calculator. So how are we supposed to be able to find this? Well, first off, let's write down, let x let's assume it's possible. Then what does that mean? Well, that means x cubed, one more than its cube. So if you add 1 to that, that has to equal x. Okay. So how do we actually go about doing this? How can we show that such a solution exists without actually finding the number? Well, the key is to use functions and try and use properties of functions. So first off, let's consider the function f of x equals, and then notice from this we can write maybe x cubed minus x plus 1 equals 0 is an equivalent statement. So let's let f of x be x cubed minus x plus 1, right? Now first off, notice that f of x is continuous. So notice f is a continuous function. In fact, since it's a polynomial, we'll even extend it on all real numbers, so negative infinity to positive infinity. So we'll have no problems for what we're going to do here. But what we'll try and use, rather than find the exact value, we can use the intermediate value theorem to show that this exists. So all we need to do, if we want 0 to be a number where this would be a solution, we would need to find a function value that's less than 0 and a function value that's greater than 0 when we plug in for x. Okay, so you actually have all sorts of choices for numbers, right? You could go from negative infinity to positive infinity. Anything will work because it's continuous on that interval. That's the key component. As long as it's continuous, we're going to go. So in this case, consider, let's take a look at an upper bound. Let's just use f of 0 because that'll be easy. So that would be 0 cubed minus 0 plus 1, and so that equals positive 1. So we found a positive number. So in order for a solution to exist, we need to find a negative value. And let's see. Let's try f of maybe negative 2. Okay, so notice that's negative 2 cubed minus negative 2 plus 1. So notice that makes negative 8 plus 2 is negative 6 plus 1. So that's negative 5. Okay, so what does that mean? Well, by the intermediate value theorem, there exists a c in the interval. And so what is our interval? Well, it goes from -2 to 0, right? Such that f of c equals 0. And that means there is such a solution. So yes. So does there exist, and this is our work? Yes. Okay. In fact, if you wanted to make it a little bit more precise, say we wanted to limit this interval down, let's adjust a little bit. So I'll write this just to give you a picture as to what's going on. Notice f of -1 equals -1 cubed minus a -1 plus 1. So notice that makes -1 plus 1, right? And so that would make 0 plus another 1, so that's 1. So we could actually limit this down a little bit more. We could say -2 to -1 by using that value. And then you could, a way you could kind of start to approximate this is, so the interval -2 to -1, right? A halfway point is -1.5. See which side that lies on, right? And then you'd have a smaller interval. It's either from -2 to -1.5 or -1.5 to -1. And you can keep on doing that until you get so close and you can finally say, okay, here's where our solution would be approximately. So hopefully that makes sense in terms of how we show it, but that's the beauty of the intermediate value theorem. It can start to tell us when there's roots or solutions to certain scenarios as well. All you need to do is find possibilities on either side. You don't even need to find the value. Okay. So now our next one. So some people struggle with using this definition of the derivative. And so I wanted to work through one and we could see how it works. So use the definition of the derivative to find the derivative of the function f of x equals square root of 3x. So first off, what is f prime of x? Well, that's, if you recall, limit as h approaches 0 of f of x plus h minus f of x all over h. So now here's the little trick to this. First off, f of x plus h, what does that equal? We know what f of x equals, so that second part's already done. But f of x plus h, that equals square root of 3. And then wherever we see an x in that original equation, we got to replace it with x plus h. Okay? So notice what that makes is square root of 3x plus 3h. And that's what we'll plug in here. So we get limit as h approaches 0 of square root of 3x plus 3h minus the square root of 3x all over h. Whew, right? A lot of work. But what this does is it allows us to see an approach for a solution. Now, the difficult part here is when we plug it in, notice we get 0 over 0. So that means there's work to be done, right? And that square root, once again, notice it's been a common theme here. The way to fix the square roots, we talked about it before, is you need to multiply by that conjugate. And so let me shorten that up just a little bit. So the conjugate would be the square root of 3x plus 3h plus the square root of 3x all over h. Oh, it's not over h, I'm sorry. All divided by the square root of 3x plus 3h all over square root of 3x plus 3h plus the square root of 3x. Okay? So what does that make up top? So limit as h approaches 0. Notice when we square, well here I'll actually write out the extra step. Once again, 3x plus 3h, the quantity squared, minus the square root of 3x, the quantity squared, all over h times the square root of 3x plus 3h plus the square root of 3x. So what does this make? This makes 3x plus 3h minus 3x. Oops, I forgot that limit as h approaches 0 part. H, and then we have square root of 3x plus 3h plus the square root of 3x. So notice your 3x's will cancel. So that one's gone and that one's gone. And so we're left with this thing equals the limit as h approaches 0 of 3h over h times the square root of 3x plus 3h plus the square root of 3x. And now your h's can cancel. And then, oh, I see a question just popped up. So we use conjugation whenever there is a square root value in the numerator or denominator. That's very close. So I'll give you an example of when it doesn't happen. So an example of when it doesn't happen. Say I have limit as x approaches infinity and I have a cube root. Or I'll keep it square root just for kicks. So square root of, let's say, x to the 4th minus 3x squared plus 7, and then I have a 5x squared minus 8. This is a case where you have no conjugation. So what's the key component? Well, the key component lies right here. You see that it can either be a plus or a minus sign. In those cases, I should say it depends. Sometimes you can have infinity over, say, 2. Well, then that's going to be infinity. But it could be a plus or a minus sign. That's when you can use conjugation. Notice the square roots are on the outside of that plus or minus sign, versus down below that square root, the minus signs and plus signs are inside that root. So hopefully that makes sense in terms of what's happening. You need that